Hi, I'm Arno Candel. I'm the CTO of H2OAI, and in this demo I'll show you how we train gradient boosting machine learning models on a supercomputer that has 8 GPUs. If you want to reproduce this, all you need is a Linux box with a graphics card and CUDA installed, preferably an NVIDIA card. And the modules that you need are all specified here. So we are importing H2O, we are starting the H2O cluster here, and we are parsing the dataset here. The dataset has 1 million rows for training and 1 million rows for testing, so it's a 2 million dataset. And it has 29 columns, which are 28 numbers and one binary label that says, is this event a Higgs boson or not? It's a binary classification. Dataset got parsed in 4 seconds onto the system. It has 80 cores, so it's a fast system, but the GPUs are actually even faster. The H2O XGBoost estimator is what we use to make these models. It can use GPUs, and you can specify exactly which GPU you want to use in a multi-GPU system. And we're using 100 trees just for benchmarking. We're not actually doing early stopping. We're not specifying a validation frame during training or anything, which you would normally do, but in this context, all we do is just train for 100 trees and see how long it takes. We also just score once at the very end, such that it's not taking any time. Now, did I launch this cell? Not yet. Okay, here we go. And now let's run this. So when we launch it, it actually launches on just 8 GPUs. I removed the 421 here, and we're just interested in running this on all 8 GPUs right now, and it's gonna launch 4x4 models, so 16 models in total. And these models are getting pushed into the H2O system as we speak. You can see that there's more models that you could build. You could build it from this flow environment. You can build TensorFlow models. You can build CPU deep learning, fully connected neural nets. You can build random forest gradient boosting models and so on. But this is the XGBoost model, which is fully featured. It has all the options that XGBoost has. It has even light GBM. It has back-end GPU and so on. It has GV linear, Dart, everything. So it's a nice method. What you really care about here is how fast this is. So let's look at the output here. You see the GPUs are still busy doing some computation. The CPUs are somewhat busy as well. So this is all going on nicely as we speak. And one thing I want to mention before we forget is that this model here that you get trained from Python, let's say, any model that gets trained in H2O always can be refreshed while it's training, so you'll soon see an update here. But since you only score once at the very end, we'll have to wait until it's done. At least you'll see how accurate it is on the training data, which is still some indication of the model convergence. And once it's done, we can actually download this model as a deployment package and we can put it in production. So we have wrapped XGBoost to be productionizable in this H2O environment where you have all these other models as well. Here we go, it's done. We have an 84 AOC on the training data. We can now stop refreshing. We have variable importances. We have gains lift charts. So for example, you can see at 3% of the top bosons, let's say that we consider bosons, what's the actual lift that we get over predicting just the background to signal ratio. There's an 84% gain. And same is true for the AOC chart. You can look at where the maximum F1 is, for example. You get the confusion matrix, everything. So this is all nice. You get the XGBoost accuracy and the speed on the GPU, but you get the same H2O familiarity as all the other models. Now, in here you saw that it took about 100 seconds to train on 8 GPUs, all these 16 models in parallel. It pushed them into the H2O store. Now that we have them in the store, we can actually extract them back out here and get a handle onto it from Python, and we can compute predictions on this test set, which has been defined here. So that's the next million rows, the second half of the data set, and we can score it right here. And then we could plot the performance scaling plot if only we had run more than just this one case with 8 GPUs. So if you want to see the whole thing, you go to GitHub and you go to our repository called H2OAI perf that shows the notebook itself and also the plot that shows the scaling. So this was the 100 second roughly for the 8 GPUs, and it goes all the way up to 400 second on one GPU or half an hour on the Xeon dual Intel chip. So in this data set for this model, it makes sense to use GPUs if you have them, and the more GPUs you have, the faster it gets. You can parallelize this task. Of course, these models are not all the same. Some models have more depth, like 12, and other models have depth 6. They're not the same in workload. Also, the sampling rate of 0.7 for columns and rows means that only half the data is used, so it's also another factor of 2 faster. So the one GPU that gets the depth 6 with sample rate 0.7 has much less work than the one that gets depth 12 and sample rate 1. So that's why it's not a linear scaling plot, but hey, it's a realistic workload and it's interesting to look at. So thanks for your interest, and I hope to see you soon.